Okay, so last week or last time we looked at two approaches to fingerprinting, right? One is fingerprinting by multiplication by a random vector, and the second type of fingerprinting was taking a modulus by a random integer. So today we're going to look at the third and last and most powerful, I think, kind of fingerprinting, which is fingerprinting by polynomials. And I'll motivate it with an analog to something that we've already looked at, which is checking polynomial multiplication. Okay, we know how to multiply polynomials. There's this natural quadratic time algorithm. You can do it quicker using FFTs if you get fancy. But suppose you want to check your work. How easy is it to verify that the product of two polynomials is equal to another? And how might you verify it? Yes?
Well, if you know the roots of each polynomial log p.
Why would I know those?
Well, maybe okay, that's true.
I mean, sorry. No, no wishful thinking. What we get is this: P, Q, and R, and that's it. How can we verify this product? Yes? Yeah. How about evaluating at a point, right? Right? And check if you get 0. Okay. Is this going to work? Or how well is it going to work? Well, under what circumstance does it not work? Right? How can we get fooled? Yes? Exactly. So again, this is a test with one-sided error, right? If PQ is equal to R, then you're never going to think that it's not, right? But if PQ is not equal to R, then what you have here is a polynomial, right? If it has degree n, then it's only going to have n roots, right? So if I pick R from a range 1 to 2n, right, the probability that I get a root is at most a half. And if I go up to 2n squared, then I can drive that probability down to 1 over n, right? So most likely, I will get if these things are not equal, I will get a non-root, and that will confirm for me that they are, in fact, not equal. Now notice that for this test, I don't need any kind of primality assumption or anything like that in R, just any old random integer. Or, I mean, you don't have to limit yourself to integers, but I will to keep things simple, right? So any old choice of random integer would work. There is the issue of the size of the numbers that you are working with. I've discussed before how we generally assume in our computer models that we can take our log n bit numbers, right, and multiply them in constant time and add them in constant time and so on and so forth. However, a number like x to the n is going to have n bits, which is going to be bigger than fits into any normal machine word and is therefore going to be expensive to add or multiply or subtract. So what do we do about that? Two possible solutions. So one solution, if the polynomials that we're working with are polynomials over ZP, right? Which is to say polynomials over a finite field, then we can do all the math mod P. Right? And in order for your, if your polynomial is not over ZP, you can still make up a P, right? If you choose P bigger than all the coefficients and the degree n, I should have used d, but then your non-zero polynomial is also a non-zero polynomial over ZP. Okay. So you can just pretend that you're working over ZP even if you weren't originally, right? This assumes that your coefficients are integers. Right, if you have real valued coefficients, things get more complicated. But we're going to be focusing on the integer coefficient case, right? So, and in particular, right, if your coefficients are fitting inside of a machine word, right, and your degree also fits inside of a machine word, then you can pick a P that is bigger than all of them that also fits in one or two machine words and do all of your arithmetic modulo that P, right? And note here that P doesn't have to be carefully chosen, or like, we did a lot of stuff with random P last time. It just has to be big enough. Right? As long as you take a P that's larger than the degree and the coefficients, you have a polynomial that's non-zero mod ZP. Now and even over ZP, it only has a number of roots equal to the degree, and therefore a random integer will reveal that it's not a zero polynomial. Make sense? An alternative approach. So this requires choosing one polynomial, one prime, and just using it, and it will work. Right? There's no error introduced by the choice of the prime. Solution 2 is to say, right, we have this non-zero polynomial evaluated at R. So we get a number, let's say a non-root, right? So we get a number of value, let's say a times n times x to the n, where a is the max coefficient. Right? That's the biggest value that the polynomial can generate. And just like last time, we know that this has only log of a n x to the n prime factors. And this is log a plus log n plus n log x, right? And so if we go back to our fingerprinting technique from last time, right, we pick a number that is bigger than twice this value, and we have a 50-50 chance of picking a number that, pick a prime that's bigger than twice this value, we have a 50-50 chance of picking a prime that's not one of the divisors of whatever this number is, right? So a random prime in the range, let's call this y. So a random prime in the range from 0 to 2y log y has a half probability of not being a divisor. So we know that if we pick a random prime that's only this big, it will probably reveal to us that we got a non-zero, that we had a non-zero number, which tells us that we had a non-zero polynomial, right? So you can either go with a deterministic prime that's bigger than all your coefficients, or you can pick a random prime in this range, and either of them will work to, with reasonable probability, detect when you have a non-zero polynomial. Okay. All right, so polynomial multiplication was the warm-up, but now I want to show you the real fun story. But in order to do that, we're actually going to do fingerprinting with multivariate polynomials. Okay. So, yes, question? If you pick R and P randomly, let's see. I suspect yes, but I don't actually think I've ever seen a proof of that. Okay. I think because most of the applications work with multivariate polynomials, and I'll show you what goes on with multivariate polynomials, and it just may be that the sort of single case became uninteresting once people started thinking about multivariate fingerprinting. So I'm going to talk about a multivariate polynomial, which is over n variables. And I'm going to define the degree of a polynomial to be the maximum sum of degrees in a term. So if I have something like x1 to the 6th, x2 cubed, x3 to the 10th, this is going to be a term of degree 19, and I just take the maximum over all the terms of the polynomial. Okay? And sorry, I should call this the total degree of the polynomial. So let me give you the Schwartz-Zippel lemma, which is the sort of multivariate analog of the n roots story that we're used to. Fix some set S. And we're working over a field F, which will be our polynomial, our prime, in general, our prime again. So fix some set S contained in F, and let each Ri be chosen randomly from the subset S. Let's call my polynomial Q of x1 through xn. So if I choose randomly for each of the xi, then the probability that I get a 0 conditioned on Q not being 0 in this field is at most the total degree divided by the size of the set that I'm choosing from. Okay. So this is a exact generalization of our story for a single variable, right? When you have a single variable, d is just the usual degree, and we know that there are d roots. And so if you choose from a range of size s, the probability you get one of the roots is at most d over s. This says that exactly the same result is true no matter how many variables you're dealing with in your polynomial. Okay? Which is a little bit surprising because a multivariate polynomial can have a lot more roots, right? It can actually have exponentially many roots. But we still get this small chance of being fooled. And I think, I mean, I can only speak intuitively here, but I think that the reason that this still works is that to counter the exponentially many roots, we're getting lots and lots of different random values, right? It's not like you're picking a single r and plugging that into all of the different x's. You're choosing a different random value for each of the x's, and that just happens to counter the exponential growth in the number of roots with the number of variables. Okay? So, proof. And importantly, notice that there is no dependence on n. It doesn't matter how many variables you have. It's still the same probability. Okay. So the proof is actually not that hard. It's an induction. Okay. I'm assuming that Q is not the 0 polynomial. So some x, let's say without loss of generality x1, affects the value of Q. Actually, I guess if Q is a constant that is not 0, then we're never going to be 0, and then we're fine, right? So we don't need to worry about that case. Now, if Q is not a constant, then it depends on one of the variables. Let's say it's x1. So let's write Q of x1 through xn as a sum. We're just going to break it out as a polynomial in x1. No. And it's going to go up to some k, the sort of maximum degree that x1 ever appears in a term with. And then for each of those k's, there's going to be some polynomial in the other variables that multiplies that term x1 to the I. Yes? Now qk that's the first term here, right? K is the largest degree that x1 ever sees in this polynomial. Qk has total degree at most d minus k. Can anybody explain why that is? This is really just to make sure you're keeping up with the definitions. Yeah? Exactly, right? Total degree bounds the degree of every term in the polynomial, right? Qk has some maximum degree term, but then you add another k when you multiply it by xi to the k. So what's inside of qk can only have degree d minus k. Okay. By induction, the probability that qk of of r2, plugging in the random values, to Rn equals 0 is at most d minus k over the size of S. Yes? Now, if qk of R2 through Rn is not equal to 0, then the sum of x1 to the I times qi of R2 through Rn is a non-zero univariate polynomial. Right? Because its leading term, right? There is a coefficient that is not 0 for the first term. Yes? Okay. That means that it only has k roots, right? Because we assumed that k was the largest degree on x1, right? So there's only a k over s probability it evaluates to 0 on R1, the random value I choose for x1, right? So this is just another example of the principle of deferred decisions, right? We're saying you assign all the different RIs, you pick all the RIs together, but in order to do my analysis, first I look at R2 through RK, and then I sort of decide what happened, and now I reveal or check what happened to R1. Okay? It's just a way of explaining the conditioning that I'm doing. Okay? And so now, up there I have a d minus k over s. Down here I have a k over s. I add them, I get d over s. Okay, wait a minute. Why can I add them? Let's just check that. The probability that I get a, well, let me write it with some general events, and then we'll fill them in. We'll fill in which events we're talking about. So if I wanted to check the probability of some event, sort of conditioning on some other event, I can break out the event according to whether event 2 did or did not happen. Right? That's just basic probability. That's less than or equal to probability of E1 conditioned on E2 not happening plus the probability of E2 happening. So I've just put upper bounds on each of these, right? So this intersection, this conjunction, is less than the conditional probability, because to get this, I have to multiply by the probability of not E2. Yes? And here, I've just said that the intersection is less than the probability of one of the events. Okay? But these are but I can sort of now read these off as the events that I analyzed up there, right? So E2 is the event of getting a 0 univariate, of getting Q2 of R2 through QK of R2 through Rn equal to 0. So here I'm conditioning on not having that leading polynomial be 0, in which case I'm looking at the probability that the univariate polynomial is 0, conditioned on not having a 0 polynomial. So this is my d over size of s term, my k over size of s term, and this is my d minus k over size of s term. So I add them, and I get d over s. Okay? So the point of this lemma is to give us some bounds that we can use to do fingerprinting by multivariate polynomials. Now, why would you want to do fingerprinting by multivariate polynomials? Well, I will show you next, but is everybody happy with the Schwartz-Zippel lemma? Yeah? Yes, go ahead. K is the maximum degree of x1 in the multivariate polynomial. Okay. All right, now let me show you the application. That was the unpleasant part of lecture. Now comes the fun part. Okay. I never like doing lots of math, but now comes the fun conceptual part. We are going to look at a classic problem in graph theory, which is the problem of perfect matching. Okay, we are given a bipartite graph and vertices per side. And we want to create a perfect matching, which is a set of edges such that every vertex has degree equal to 1. Right? So essentially, the only way to do this is to pair up the vertices on the left and right sides of the bipartite graph. Right? So each vertex on the left has to have something going out and has to reach somewhere on the right, and it can only reach one thing on the right. Okay. Classic problem in graph theory, many real-world applications, and a lot of beautiful theory behind it as well. Okay. So the standard algorithm for this, well, there are many actually, but the one that I taught you last year in advanced algorithms was based on what? Anybody remember? I don't think I have a completely new class. Yes? Exactly, right? You do max flow. You set up your bipartite graph. You put a source on one side, put a sink on the other side. You put some directed edges. It's important that they be directed. We actually got pretty tripped up on a research project once when we forgot that they had to be directed. But if there is a perfect matching, then there is a flow of n disjoint paths from S to T. Conversely, if there is a flow of n disjoint paths from n to T, in order for them to be disjoint, those paths have to be paths of length 3, and no two paths can share a vertex. Right? So this can be solved by max flow. Okay, we are going to explore a completely different way of solving this problem, which does not win on runtime, but absolutely wins on coolness, and also has some really remarkable applications, which we will get to in this lecture and next lecture. Okay. What we're going to do is look at a representation of this problem called the Edmonds matrix. The Edmonds matrix is basically the adjacency matrix of the graph. Okay. But instead of putting a 1, you put a variable. We'll call it xij, right? So if there is an edge from vertex I on the right to vertex j on the left, then we put in the term xij. If there is no edge, then we just put in a 0. Everybody understand the matrix? All right. What Edmonds proved, or actually I don't know if Edmonds proved it, he probably did because he came up, because the matrix is named after him, is that there is a perfect matching if and only if, let's call this matrix M, if and only if the determinant of the matrix is not 0 as a polynomial. Okay. Notice that this matrix, right, we put a bunch of variables in it, so its determinant is a polynomial. Okay. And Edmonds, and the key result, which I believe is due to Edmonds, but I should check, is that there is a perfect matching if and only if that polynomial is not the 0 polynomial. Okay. What is the proof of this claim? Yes, blue shirt. Exactly. This is, what is this called? The Cauchy, is it the Cauchy something? What was that? Yeah. The point is that determinant of M can be written as the sum over all permutations of -1 to the sign of the permutation, right? Whether it's an even permutation or an odd permutation, times the product from I equals 1 to n of m sub I pi of I. Okay. In fact, if you think about it, a permutation is a candidate perfect matching, right? It's basically assigning each number from 1 to n to a different number or to a distinct number in the range from 1 to n. Some of them might be the same number, right? But there is this assignment, right? And so essentially, for each of those permutations, you can now ask, is there a perfect matching corresponding to that assignment of left numbers to right numbers? If there is, then all of the variables in the Edmonds, all of those entries in the Edmonds matrix will have variables in them, right? Which means that you'll get a non-zero term in this great big determinant formula, right? If, on the other hand, there is not a perfect matching, it means that one of those edges is not present, which means that the corresponding entry in the matrix is 0, which means that this product will be 0. And so you will not get one of those terms. Right? Now, also, because we put a different variable into each of the matrix positions, no two terms will cancel each other, right? Every pair of terms involves a different collection of variables. So this is essentially summing over all of the perfect matchings, the product of the variables involved in that perfect matching. Yes? Exactly. We're actually calling these x's right now are variables. They're not numbers. They're why am I losing the word? They're indeterminates, right? They're symbols. X, xij. Okay, and we're looking at this sort of symbolic formula and saying this symbolic formula is a polynomial. Okay. What can we say about this polynomial? How many terms in this polynomial? Yeah? So that's the number of non-zero terms. And how big can that be? Yes? Yeah. Boy, this is a big polynomial. Won't want to work with this polynomial. This, right? Can't write it down. Right? Oh, but wait a minute. What's its degree? Total degree. It could be 0, that's true. But if there is a matching, what does that do to the total degree? How come? Yes, and each of those variables has degree 1, right? So the total degree is n. Every term has the same degree, n. Okay? All right, so we've got this gigantic polynomial. God forbid we ever write it down. Okay? But it is a low-degree polynomial. Okay? So this is the problem with multivariate polynomials, is that they could have lots and lots of terms in them. Okay? But it's low degree. So what does Schwartz-Zippel tell us? Right? Schwartz-Zippel says that if you work mod some prime p, which is bigger than n squared, okay, right? I'm going to do that in order to keep the error probability small. That implies that if I have a perfect matching, then the determinant of the Edmonds matrix is not equal to 0 in ZP. Yes? I actually just need the prime to be bigger than n, because that's the total degree, and all the coefficients are 1. Okay? So now if I pick a random values Rij from that range, 0 to p, yes, then the probability that the determinant of m with xij replaced with rij is equal to 0 is at most the total degree, which is n, divided by my polynomial, my range, which is bigger than n squared. So there's only a 1 over n chance that if I put random numbers into the polynomial that I've created, that I will get a 0 value mod p. Does this make sense? Okay, so that's nice, but I mean, this polynomial is huge, so how could I evaluate it? That's a trick question. How do I evaluate this giant polynomial quickly? Yes, what's your question? No. I mean that the determinant of m is not the zero polynomial, as a sort of symbolically as a polynomial. Okay? Yeah, that's an important distinction. But what we just concluded is that because it's not the zero polynomial, when we put in random numbers, it's probably not the 0 value mod p. So how do I evaluate this polynomial? Yes? It's a determinant. So just compute the determinant. Right? We can check whether there's a perfect matching by just throwing random numbers into the adjacency matrix and computing the determinant. That is probably not something that you thought of when you walked into class today. Yes, question?
So how do we evaluate the determinant facts?
Well, we can do that using our typical algorithms for determinants, right? And now we're doing, this is doing mod z, this is doing integers mod p, so we don't even have to worry about stability and round off and real numbers and so on and so forth, right? We just do the usual trick of triangulating, of eliminating entries in the matrix until the determinant reads out, right? It's this, yeah, that's in your linear algebra class, right? Yes? Not really, because these Rijs are not 0 and 1, right? If I picked some random 0s and 1s, you could sort of say I was looking at the edges where I had picked a 1, right? But that's actually too small a range for this to work, right? I have to pick from the range up to n squared, or at least up to n, or 2n, in order to have a decent chance of this working. Okay? If you really use zeros and ones, then essentially what you'd be doing is discarding a bunch of the edges and checking if there's a perfect matching in what's left, which there probably won't be. Or, I mean, it's depending. Yes? Great question. Another weird thing about this algorithm is that it tells you there is a matching, but it tells you nothing about where it is. Right? Now, this is not uncommon. There are many algorithms that can be used to detect the existence of something without telling you where it is. And there's a nice standard trick for turning one of these existence checkers into a constructive algorithm. And that's something called self-reducibility. And I'm not going to define it, I'm just going to demonstrate it. So we've got this algorithm that tells us whether a graph has a perfect matching. We want to take a graph and construct a perfect matching, right? So the only thing we have is this perfect matching tester. How can we use this in order to actually find a perfect matching? Yes? Exactly. We just throw edges away until we eliminate the perfect matching, right? So assuming it has a perfect matching, let's discard edge 1, right? If we still have a perfect matching, we just continue, right? We have a graph with a perfect matching with one less edge, progress, right? If there is no perfect matching, what does that tell us? Yes? Yes. In fact, it tells us E1 is in every perfect matching. Right? Because if there was any that didn't have E1, there would still be one. Right? So set it and its vertices aside and continue. So we go through the edges one at a time. For each of them, we decide what to do. Once we've gotten through all of the edges, we will have set aside a perfect matching, and we're done, right? So overall, this requires m perfect matching checks, i.e. m determinant calculations. Right? And this is not great. This is going to give you a runtime of about m times n to the 2.376 if you use the fanciest matrix multiplication / determinant algorithms, which only dominate runtime-wise when n is bigger than 100,000 something. But it is polynomial, right? So we have a very weird polynomial time algorithm here. I haven't thought about it, but you can probably update the determinant incrementally instead of having to recompute it each time, which might give you a little more speed. Sorry, yes, I misspoke. So not great for practice, but very beautiful and interesting. Yes? Okay. And we will shortly be moving to a study of parallel algorithms, where this technique is actually the best technique that you can use if you want to solve the problem in parallel. The max flow approach does not parallelize, and this does, and we'll look at that next week. Any questions about this bipartite matching algorithm? Yes?
Is the existence algorithm that you showed faster for just determining existence than Maxwell?
Not anymore, because there's been amazing progress on MaxFlow, and there is this paper which is like 100 and something pages long, which gives a MaxFlow algorithm with a near linear runtime.
Very interesting.
Yes, it's not an easy algorithm. It's the n to the 2.376 bound is better for dense graphs than the classical MaxFlow algorithms, but that's not really a fair comparison, because the n to the, like, if you're talking about practical algorithms, then practically speaking, MaxFlow is probably going to be faster than determinant. Actually, it depends on the, probably depends on the sparsity. I'm not sure. If you're talking about weird algorithms, then this weird MaxFlow algorithm is faster than the weird determinant algorithm. Okay? Other questions? Okay. We'll take a break, and then I will show you an application of these determinant ideas to network communication.
But also, or the main thing is to like, I'm kind of curious how fast the approach that you're supposed to find in the class. Or like, how does it compare to like my although like also like how much faster it saves compared to like Python. Then why do you use wow. You know, and my approach did not use elliptic curves. I know where that comes from. But yeah, I like made a basically I like prepared a proof being recorded.
All right, let's talk about network coding. So some of you in this class may have done a lot of computer networking. Some of you probably done none at all. But I'm assuming all of you know that the internet is just a great big graph, right? With lots of wires connecting lots of routers. If you want to support internet communication, a natural way to think about it is that I've got a source node that wants to send data to a sink node over graph edges of some fixed capacity. Okay, and so if you want to determine the maximum possible throughput, the maximum rate at which you can send information from the source to the sink, what kind of algorithmic problem are you solving? Yes? Max flow, right? Right, I've got my graph, and I can send messages along various edges. If we assume that each edge has a capacity of 1 unit, one byte per second or something like that, right? However many disjoint paths I can find through this network, I can send a stream of information along each of those disjoint paths, and that will represent the amount of information that I can send through from S to T per time step. That means that the max flow determines, right, the ST min cut / max flow determines the number of disjoint paths that I can have, and therefore determines the throughput that I can achieve. Yes? I'm going to ignore issues of delay, of latency here, right? I'm just worrying about the throughput, how much can actually be sent, and not how long it takes to get there. So that's great. A downside of this approach is that in order to do it, you have to compute a max flow, right? And that may be hard, especially because the network keeps changing as links come up and down and so on and so forth, right? It requires a lot of global coordination to actually compute that max flow. Okay. Now, this is the most basic case of just one sender and one recipient. But you can also talk about multicast, which is where you want to have many recipients. Of the same content. Okay. A good example of this is Netflix, right? There are God knows how many people who are all trying to watch The Hunting Wives at the same time, and right, you want to deliver the same information to all of those recipients, right? So this is a much more complicated question, right? I mean, you could just solve the max flow problem to each recipient, and obviously you're only going to be able to send this information if each recipient has enough capacity to receive it, right? The ST min cut or ST, now you've got many recipients TI, right? So it had better be the case that each of the TIs has sufficient capacity to receive the information from the sender, right? But if you just do the delivery to each of the recipients separately, it feels like you're going to be potentially wasting a lot of capacity, and you might not be able to do it, right? Intuitively, it feels like maybe if TI is here, well, actually the easy case, right? If TI is here and TJ is here, then you should just send it all to TI and then have TI pass it on to TJ, and now you can serve both of them with just as much capacity, using no more capacity than you did to just serve TI, right? Even if you've got another TK over here, you can hope to share a lot of the bandwidth, right? Since you're sending the same information, or you might imagine that you could. Okay. So the dream or the ideal would be that you can multicast to all the recipients if you can unicast to each, right? Having enough capacity to reach each recipient is necessary. Maybe it is also sufficient, Unfortunately not. Okay. So here is a simple example. I've got my source up here. And I have, let me see, how do I draw this? Yes. I have a source which wants to send out two pieces of information. Let's call them X and Y, right? And I have these two recipients, T1 and T2. Okay? Now, it should be pretty clear that I have enough capacity to send X and Y to T1, right? I can send X this way, and I can send Y this way. Right? Let's assume let's keep all the edges directed so we don't have to think about things going back and forth. Similarly, I can also send both pieces of information to T2, right? I can send Y this way, and I can send X this way. However, I cannot send both pieces of information to T1 and T2, right? Because right here, that essentially involves sending 4 pieces of information, and here there's a cut of value 3, right? So either 2 of the edges have to carry X, or 2 of them have to carry Y, and so 1 piece of information does not get through. Okay? Yes? But here I can't. That's what I'm saying, right? So this is a single counter example, not a general claim. Okay? But this shows that it is not always possible to multicast just because you can unicast to all the recipients. Okay? If we continue to talk about network communication the way we have been so far. Yes? Yes. In other words, S is trying to send both X and Y to both recipients. Okay? Okay. So getting around this requires a change of perspective. And there was a seminal paper by Alswade et al. Oh, so I should say, this is something of a war story, because the reason I decided to teach you this half hour is because it's a nice example of, if you know the right theory, then you can make useful contributions in other areas. And so this is a place where our theory ideas had a nice impact on networking. Okay? So Alswade et al. Had this seminal paper which introduced the idea of network coding. They said that the nodes in the internet are not stupid. They are complete computers. So they don't need to just pass data along. They can compute as well. Okay. So he proposed that you should let the intermediate nodes compute alternative values to send, or alternative messages. That could be sent on. You don't need to just copy the messages that you receive. Okay. And in particular, he's the one who came up with this example. Imagine if, when this node received X and Y from the 2 different paths, what it passed on was the exclusive OR of X and Y. Okay? What does that mean? Well, now T1 is receiving X the normal way. It can receive the exclusive OR of X and Y, and now it can reconstruct Y. Similarly, T2, which is receiving Y the normal way, can along this path receive the exclusive OR of X and Y and recompute X. So by having this node do a little bit of computation, you've suddenly increased the multicast capacity of this network. Is that clear? And so Alswade actually proved that with this kind of network coding, you can multicast to all the recipients who have enough capacity to receive the unicast. So the max flow min cut condition by recipient is both necessary and sufficient if you do network coding. Yes? That's the question. What Alswade proved is that there are functions that work. Okay? There was follow-on work. I may get this backwards, but I think Li et al. Showed that linear functions suffice. So they basically demonstrated that you can work in the domain that we've been talking about, where you think of what's being sent as integers, and the nodes just compute linear combinations of the integers that they receive and pass those on. Okay? But this was existential. Okay? Ralph Cotter and Muriel Medard, who works in Building 36, they gave the first polynomial time algorithm. Okay. And this is the first computer science paper I've seen that mentions Hilbert's null-Stellensatz. And it also uses something called Grosvenor bases to actually compute some appropriate linear functions that achieve this network coding bound. Okay? And I happened to be at lunch with Muriel one day, and she tried to explain it to me, and I couldn't understand it. So I asked her if maybe there was a simpler way to figure out what would be good linear functions, good ways to take linear combinations of incoming messages so that the resulting output could be decoded as desired at each recipient. So let's see if we can derive that by looking at a particular relevant communication network. I'm actually going to start with the unicast story. Okay. I'm going to draw a very strange-looking communication network, but that could conceivably arise in practice. Let's just suppose that our communication network happens to look like a bipartite graph. Okay? And let's suppose that we know that there exists a perfect matching, and therefore the capacity of information from S to T is n. Okay, there are n disjoint paths from S to T. Okay. The work on network coding demonstrates that if you pick the appropriate linear functions, right, essentially S has n messages, and it computes some linear functions that it passes on to all of the intermediate nodes, right? Now, these nodes only receive one message, so there's not much point in doing anything with it. They'll just broadcast it on to all of the nodes that can receive from them, right? Now, these nodes will have some incoming messages, and they will compute some linear combination of the incoming messages and pass that on to T. Okay? And so T is going to receive a bunch of linear combinations of linear combinations. Yes? That's what network coding would do. So let's figure out how we would represent that, right? So S has these n messages, right? So I'll call those x1 through xn, right? And what's going to happen is that S is going to generate some linear combination of the messages for each of the vertices that it's sending to. That means it's just taking a dot product, right? And so I can represent what S is doing by a matrix, right? And this produces a vector of sort of left-hand sides. Right? Actually, sorry, I made this too complicated. I don't need linear combinations at S. S is just going to send its end messages here. There's no point in changing them. Each of these nodes is going to receive multiple messages and compute a linear combination of them to pass on to T. Okay? So this node receives messages from vertex 2 and vertex 3, and it takes some linear combination of them. This node receives the messages from vertex 3 and vertex 4 and computes a linear combination of them and sends it on. Okay? So if you think about it, I can represent that as basically putting a coefficient onto each edge, right? So I'm basically going to put a coefficient per edge, which is what this node is going to multiply the message that it receives on that edge by, right? So if this is vertex I on the left-hand side and this is vertex j on the right-hand side, I'm just going to call the coefficient on this edge xij. And that means that this vertex is going to compute, right? So right-hand side vertex j computes a sum of xij times what I'll call message I, right? Whatever is received at the ith left-hand side vertex. Yes? So I can also, and so now T receives the vector of all of these, right? So notationally, the way I can write this is that I have these n messages that arrive at the n left-hand side vertices. And each of them gets multiplied by coefficients xij. Of course, many of the coefficients are 0 because there isn't an edge from the left-hand side I to the right-hand side j. But wherever there is an edge, I get to multiply by some coefficient, and then I sum those up, and then I send that on to be received at T. Is some other collection of, is some other vector of messages. Yes? So, sorry, I made it complicated first, but is it clear what's going on now? That essentially the bipartite graph defines a certain matrix of coefficients, and this is called the transfer matrix. Because it describes what happens if the source sends a collection of messages, what is received by the sink. Okay, and we have a transfer matrix because we are using linear functions to do the network coding. Okay, so any questions about what we've set up here? So now comes the big question. Under what circumstances will the sink be able to reconstruct the messages? Okay. Let's call these messages Q1 through Qn that it receives, right? So under what circumstances can the sink reconstruct the messages M, and how should it do so? Yes? Exactly. So the sink can recover the original messages as the inverse of the transfer matrix times what it receives. Yes? Because what it receives is just the application of the transfer matrix to the original vectors, right? Now this works as long as the transfer matrix has an inverse, right? Under what circumstances does the transfer matrix have an inverse? Basic linear algebra question, right? Yeah? Right. Non-zero determinant. Okay. Given where this transfer matrix came from, under what circumstances does it have a non-zero determinant? How did we make this transfer matrix? We put an xij term, a coefficient, everywhere there was an edge. Does that remind us of anything? Yeah? So long as the graph has a perfect matching, right? If you have a perfect matching. Okay? Because in this special case, the transfer matrix is actually just the Edmonds matrix. Right? So if there is a perfect matching, then symbolically the transfer matrix has a non-zero determinant. We have just proven that if you throw random numbers into that transfer matrix, you get, with high probability, a matrix with non-zero determinant. Which means that if you just throw random numbers, random coefficients, onto these edges and use those to compute the messages, the linear function messages on the right-hand side, you will be sending something that can be reconstructed by the sync to get the original messages without ever finding the perfect matching in the graph. So no Maxlow computation or anything like it. Okay. Yes? Sorry, what was that? Yes, but that is a local computation, right? And so there is still a thing I have to fill in, right? If I just pick these random numbers and use it to send data, T doesn't know enough to invert the matrix because it's only receiving a weird function, right? So you need to tell T about this transfer matrix. One easy way to do that is that first is to just send, right? Each round that S is sending is an n vector, right? So just send n basis vectors, right? So when I send the first basis vector, what's going to be computed here is the first column of the transfer matrix, right? So if I send n basis vectors, then the sync is going to receive the n columns of the transfer matrix, and at that point it can invert, and now it can proceed to, right? So there's sort of a setup time where you send these basis vectors for n rounds, and once T has received those, now you can send whatever messages you want, and T can proceed to reconstruct those messages from this transfer matrix. Okay? So I don't know, for me, this is like why we study algorithms. It's because that way we know how to throw certain things at a problem in ways that will generate something useful, right? So, once Cotter and Medard had sort of developed this whole machinery and said, yes, you just need to have linear functions, right? You just need this matrix. Well, we already had the whole analogy in this perfect matching algorithm to demonstrate that this actually works for, that random linear network coding actually works. Now, I've only demonstrated it to you for the specific case of a perfect matching network, but this actually works in arbitrary networks, okay? Let me, so I only told you about a single sink, right? But you can generalize this without even leaving the perfect matching story behind, right? If you say that, you know, S wants to send K messages and you have multiple sinks, and between S and each sink, there is a capacity of K, which means that there is a perfect matching between the vertices that S can reach and the vertices that the sink can reach, right? Then the argument that we just made tells you that random linear coding will allow that particular sink to decode its messages, and that will, of course, apply to all of the different sinks. So this demonstrates that multicast works under random linear network coding in this bipartite graph example. Yes? So in the more general case, S will need to take a linear combination of its K messages and send a different random linear combination to each of the left-hand nodes, okay? That's why I actually went off on the wrong, on a tangent at the beginning, okay? Sorry, was there another question? Yes? Mm-hmm. Yes, that works for general graphs. And you're going to prove that on your homework this week. Okay? It requires an interesting generalization of, right, the Edmonds matrix approach applies to, it's sort of working in this bipartite matching graph, which is just sort of one layer. There's a generalization of this sort of determinant idea to graphs of many levels, where you, instead of looking at just edges, you look at whole paths from one side to the other, and that's worked out in the homework. So by the end of the homework, you'll all have shown that random linear network coding works for arbitrary graphs. Okay? All right, that's a good place to stop. Next week, we will be doing parallel algorithms, and actually I'll start by talking about how you solve the bipartite matching problem in parallel using this matrix idea, and then we'll look at some other interesting parallel problems like independent set and shortest paths.